Hello, good evening, everyone. I hope I am audible. We can start the session now. If you have any doubt from previous session or any of the session, you can ask because I think there are very few weeks before your exams and yeah, before finishing up this course. Yeah. Hi. Yeah. Okay. 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 Uh, okay, so direct and indirect band gap semiconductor. So, like last time, which I explained, right? So, let me just open this. This one, right? Okay. So, yeah. Basically, for like when you basically like so like to decide whether your semiconductor is direct or indirect. So one is direct and other is indirect. So basically what you do is because your semiconductor crystal or any solid is just periodic arrangement of atom, and you can just solve for Schrodinger equation of this potential of these atoms by uh, this like considering the repetition of these atoms, and you can solve the Schrodinger equation for this, and you can make some approximation. Okay, so someone posted I have week 5 question number 9. Okay, okay, I will just note it down. So I will clear after this. Yeah. So this like periodic arrangement of atoms basically leads to the formation of bands actually. So this like the some approximation is there that is like solved by this chronic penny model. So what does this tell? Like if you take like this potential which a Coulombic potential which electron sees around this nucleus or core atoms, and because of that like periodic potential, electron does not move in freely actually. Electrons move in under the influence of this potential. So this potential you can approximate by this periodic rectangular potential, and because this potential if you try to solve for significant number of atoms, this is very hard problem actually. You can't solve numerically. So basically or in analytically also it's quite difficult problem. So basically you make the approximation by that assuming that these Coulombic potential are equivalent to your rectangular periodic potentials, and then based on that assumption you based on that approximation basically you form a band actually. So that's why like that so in the solution of those chronic penny models, there are some states. So ideally so if you take the free electron which is not influence of any potential, it can take very like any number of energy, like there any like any value of energy is possible. But as you give put a electron in a periodic potential or under the influence of a periodic potential, and then you solve the Schrodinger equation, then basically what happens is like your electron does not see like electron, that energy level will be confined. And if your electrons so based on that those confinement actually, so that is described by bands actually. So the electrons is so for different value of moment like this is the k operator. Basically this is related to momentum. So the momentum you can calculate as h bar k, and this is the moment of electrons in a crystal. So based on this, the k value of this, the based on the this periodic potential, electron can take certain k values, and for a certain k values, the energies like certain energies are not allowed. So based on that, basically it forms a potential like this. It forms a forbidden back gap actually. So and this relation, if you draw this relation for like 3D volume, that is known as the band structure. So band structure is basically so this is known as the band structure. So basically band structure is the relation between energy of the electron and the crystal momentum k it can take. So that for to analyze any whether whether your semiconductor piece of semiconductor you will do will be follow a direct band gap, or so the the idea of if you for a different material you can calculate the band diagram actually. So this band diagram is actually is a branch of condensed matter physics and or devices. So this is solved by this density functional theory. So you can calculate or simulate, or you can just numerically evaluate the band diagram, band diagram of different material, different combination of materials with the density functional theory. So basically band diagrams are nothing but the solution of your calculations if you do with the density functional theory uh, for the arrangement of this atom. So basically, like that solution. So now for certain material, what happens is, so like this band diagram actually this follows this kind of relation. This is for 1D crystal if you take. So like now these like now for a finite crystal, there are in this whole branch, actually there are finite number of state which are allowed actually. So there are finite n number of states which are possible. So each level there are n number of states. So now like when you put a so this is the band structure. Now if you start put filling these levels, so what happens is some electrons, if you start filling the electrons in these levels, so initially let's say these are empty level. Once you start filling electrons in these levels, so this each levels has n levels. So if you start filling electron, then last state which you keep filling, suppose here, in the last stage basically what has happened, the just last fill state and above state will be completely unoccupied. So there is a possibility that some of the electrons here will at room temperature will jump through this and form the occupies the topmost unoccupied state actually. So they are basically like in the room temperature is thermal energy because the at room temperature there is a finite thermal energy kT, which can which can move this top level electrons to the bottom of topmost unoccupied band. So that band basically, and this other electrons, these electrons are completely filled actually. So only this top level of electron will top level of highest occupied band will be partially filled, and top level bottom level of highest unoccupied band will be partially filled actually. Most of the states will be unfilled and fewer will be filled. So that is and this band is known as the conduction band, and this is known as the valence band. So that if you draw the band, so that let me draw it again. So if you draw that band, so this is E, and you assume that bottom levels are completely filled. So and uh, and like this like the parabolic band you are drawing, because like at the very near to top of the valence band, you can assume that ek relation is nearly free actually. So you are considering like these have the like the these atoms has the different levels, and you are considering basically not the core levels. You are considering upper few levels actually, which are influenced by the Coulombic potential, but not so strongly that like their motion is so their motion is nearly free, but not completely free. So those are known as the conduction bands electron. So now for certain material, if you solve for this, uh, uh, if you solve this density functional material for suppose silicon and gallium arsenide, you will find that for silicon, the topmost unoccupied band and bottommost unoccupied band will not lie at the same k value. So suppose you this is uh, the uh, uh, bottommost topmost most partially occupied band, and let's say this is the like this is the no, this is the bottommost this is the topmost, and the this is the uh, topmost partially occupied band. So this is partially unoccupied, and this is partially occupied band. So there will be very few state in this band. So this band will have all the states possible. Like this is the, let's say the possible states are possible. Let's say in this these states are possible. Yeah. Band follows Coulomb's law in what? Like how you are saying like Coulomb's law. Uh-huh. Uh-huh. Yeah. For up and down, what? Uh, can you repeat? Yeah. So this gap you are talking. Huh. And- huh. Hmm. So what? So because this see like this two things are there at like the electrons is influence of the Coulombic potential, and also there is a periodic potential. So that is not isolated Coulomb's potential actually. It is it is due to the periodic arrangement of atoms actually. Is that clear or is it doubtful? Why periodic? Because you suppose you take the atoms. Let's say you take the silicon crystal. Let's say so it follows that diamond cubic lattice. So let's say this is your crystal. So let's say if you take simple cubic structure. So as you know that you have studied the solids. So each so if you take simple cubic structure, so each like corner there will be a atom. So here will be atom, here will be atom, here will be atom, here will be atom, here will be atom. So this is the arrangement. And if you repeat this crystal, so basically crystal is the repeated arrangement of this unit cell actually. So now this is the unit cell. So like here the atom will get repeated actually. So here also after something then some atom will be there. After some distance some atom will be there. So since this is following the periodic, and each atom has each atom has a it's due to its nucleus or inner core shell electrons. it has a potential actually. So that potential, if you place nearby atoms, so those potential of two nearby atoms, you will see like the, if you want to write, let's say two charges you have given. So let's say two positive charges have been given. If you want to, let's say this has a potential inversely related to 1 by r, and this is also has a relation to inversely proportional to 1 by r minus r1. Let's say this is r minus r1 and this is r minus r2. So this r2 is the central coordinate of this. So the total potential will be at each location will be sum of this coulombic potential at each point. So that basically, if you have n number of atoms, then the total potential due to those n number of atoms will be sum of these individual atom potential. And if you, as soon you bring this atom closer and closer, you will see like the this the atoms total net potential of the your arrangement will be impacted by how many number of atoms, how close they are. That's why, like, or and in a crystal actually the atoms are quite at the quite smaller distances actually. So is that, yeah, is that clear, like why do we take the periodic potential? Okay, so basically, so if you solve for certain number of certain elements or certain, for silicon, if you solve the density function theory, so basically the arrangement will look like this. So just wait. So if you take periodic arrangement of atoms, so you start filling from the bottom because electron will occupy the lowest energy first. Then you will fill. Then you will fill. Then you will fill. Then you will fill. So at 0 Kelvin temperature, because there is no thermal energy, then all electron will be occupied. But if you have like at room temperature, if you are operating, then some of this top of the valence band will be occupied by the electron will jump from here to maintain the neutrality condition, and they will be occupied in this band. So now, as you can see, like the so to have a transition from top to bottom, you should have a direct transition actually. So see, like the state just below this electron is occupied. Let me draw it clearly. Here also you draw a state. So let's say this state is already occupied. So you see, like in the direct band gap semiconductor, like the just the state just below, like, and this is the finite k axis if you draw the line vertical. So as you can see, like if your like these parabolas are shifted, so the state just below the electrons in the conduction band is corresponding same momentum state in the valence band is occupied. So there is no state to have transition actually. So electron can get transition to this unoccupied stage only. But this transition to here requires this k to be changed actually, and that can't be provided with the photons. Yeah. Now you understand, right? Yeah. Okay. Okay. So let me clear it out. Someone AJ has down week 5 question number. Uh, uh, so someone has a doubt week 5 question number 6. So uh, so week 5 question number 9. So is this your doubt is current assignment or previous assignment? Uh, yeah, yeah, previous assignment which I solved, right? Okay, okay. So this one, na. So this is in a reverse bias. It change in temperature result in shift in the reverse saturation current. Choose the correct relation, right? Okay. So, what is your doubt in this? Mm-hmm. Huh. Yeah. Mm. Uh, you think the answer will be square root and I? Uh, uh, mm, but JS is not proportional to square root and I actually. JS is proportional to square. Uh, okay. So basically, so yeah. So how you drive the current basically. So, this to drive this JS relation, basically, you need to solve the drift diffusion equation actually. So, let's say, so if you draw the band diagram actually, so this basically your this current equation actually comes from uh, so basically, what happens in the PN junction is your your let's say this is P type and this is N side, and you have the majority carriers are holes, and here majority carriers are electrons. So what happens is the uh, if you apply a potential, actually if you assume depletion approximation, so depletion approximation, so there will not be any like carrier generation or recombination possible. And this region you depletion approximation, you also assume that this region now is free of any charge carrier. So this region does not have any charge carrier. So and if you assume that there is no thermal generation and recombination, so how you will be the this so if you draw the current, so if you draw the equilibrium band diagram or equilibrium concentration, so basically you will find that like your so basically total current Js you draw due to Js due to drift plus Js due to diffusion. And diffusion you draw by like that's q times dp multiply by dp by dx uh, uh, plus or minus dn sign may be different, but dn by dx. So if you like, so basically P is the concentration and N is the total concentration. So if you want to drive this current equation, so basically and this so yeah, so basically if you want to drive this current equation, so you calculate this equilibrium charge profile. So like as in the equilibrium, some like after your depletion is reached, there will be in equilibrium electron will be going inside in this region, and same holes will be going in this region. So the profile, if you see like the if this is the electron profile is P, N naught is the electron profile, or N P naught. P naught is the equilibrium profile in this side, and here this is the P naught, and here this is the N naught, and this is the P N naught. So if you plot this profile basically, so what will happen is like if you draw this profile, so some of the carrier, if you calculate the equilibrium profile, so basically this profile will look like this. So inside this, because like the like as you join to two pieces of semiconductors, basically your some migration will start to align the Fermi level. At equilibrium, you will have some gradient, and we assume the depletion approximation. So there the carrier concentration inside this will be same, and after this you can join this line and it will follow this equilibrium concentration. Similarly, you can write for the holes here. So uh, holes will recombine there to form this kind of profile, and this may not be same actually, because if and this is the hole profile inside this, and that you can join by this. So at any point you can calculate the current. So basically, at so total current I or Js, if you divide by area, so it's equals to Ip plus In, and Ip is Ip drift plus Ip diffusion. So and this here also In drift plus In diffusion. So when you calculate the current actually, so if you calculate this reverse saturation current under the equilibrium, so you can calculate the current anywhere, but if you, so basically to calculate the current you need this slope with respect to x, dp by dx and dn by dx, that you will calculate at here. So either you can calculate at x equals to xp. So basically you can calculate the minority current profile in this direction at here, and minority current profile in this direction at here. It's just the convenience, you can calculate the current from anywhere. So based on this slope, actually there is terms comes because this there will be a term of this np naught, and that np naught will be equals to the ni square. Actually ni, that is like the minority carrier. If you write the law of that action, p times n equals to ni square. So if you calculate, suppose p in p naught, n is p naught region, that is equals to ni square. So the electron concentration in p region will be equals to ni square divided by the doping concentration na. So this ni square terms comes from here actually. So when you write this equation, and for a potential, you will see that there will be a terms time like this time there will be a terms of exponential of q of VB applied potential by kT minus one terms will come. So is that clear, or it's not clear, or it's vague? So TC and TD was in a problem. Just wait. Okay, just wait about this. TC and TD was so. So in this problem, actually, Tn plus the varying temperature. So so these temperatures are two temperatures are given, two characteristics are given. One at Tc temperature and other is this temperature. So in this plot, Tc and Tc are like the when you put it the reverse bias diode in this configuration, actually the Tc is like the uh, temperature corresponding to this curve, and Td is the temperature corresponding to this curve. So is that clear? So Td is the temperature corresponding. So Td, so basically, you need to find like if your reverse saturation current increases, then you need to find what is the relation of the temperature actually. So is that clear? Question. Huh. Okay, just wait. TC, So basically, see, like this, your Js is proportional to Ni square, like your reverse saturation current. So basically, how it will come? So your total current is given as Js time exponential of QVB by KT minus 1. So this is to your total current equation. So this and like when you apply in the reverse bias, this term, because the applied voltage is negative, this term goes to 0, and your J is equals to Js, and your Js is basically equals to uh, Q dp some relation by Nd, and times Ni square actually, plus so this plus Q dn Na, and multiply by this Ni square terms come. So Ni square, as you know, is proportional to minus exponential of minus Eg by 2kT. So as you increase the temperature, so as you increase this term, so this Eg by 2kT term will become larger and larger. So that means your Ni square will get increased. That means your Js J total, which is equals to the Js, will also get increased. Is that clear? TC is less than TD. Okay. So okay. So basically so now like so now see, like this Js is proportional to Ni square, that is proportional exponential of minus Eg by 2kT. So now one, so you see, like for C the current is lower, so this has the lower current, and TD has the higher current. You need to find which one has the higher temperature, right? This is the problem. Yeah, right. So now basically you need to so basically like this has the lower current, this has the higher current. So basically you need, based on this relation, you need to find which temperature it can be at. Yeah, yeah. Week, yeah, yeah, this is only the week 5. Yeah. Hmm. Okay, just wait. Yeah. So this so oh, this is not okay. The week 5 is this one only, na? Okay, so can you have that question? Can you post in the chat? Can you have a screenshot of that question? I have not seen it. Yeah, just post in the message chat. Yeah. Yeah. When material is direct or indirect, actually like the exact calculation you will know from only if you simulate that, like those are like those atomic orbitals and those covalent bonds, and those the calculation, those calculation, if you see like the band structure calculation you do, and even you can measure those band structure and Fermi surface of different materials. So those like based on those results, people make an assessment whether it will be a direct or indirect actually. So like people do calculation, basically those are density functional theory calculation in simulation, and you give the different properties, different group theory, like even this arrangement of atoms also matters, like which crystal structure is follows, what kind of the crystal structure follows, what kind of unit structures, like hexagonal or close pack structures, or like there are different like way, and those combination actually result to your density functional theory calculations. Uh, yeah, so it's basically you can as like you can, for now I think you can like calculate like you can like think it as a like combination of how your atoms are arranged actually. So exactly you need to solve those Hamiltonians and like those potentials you can solve actually. So based on like how close your atoms are, how much is your lattice constant. So basically different material lattice constant is different, and different elements have different number of outer shell electrons, and that will lead to different potentials, and different arrangement will have different atoms have different radius actually. The outermost most electrons has a different radius size. So based on that you do density functional theory, like real atoms radius you put, and then you do the density functional theory calculations, and you calculate that ek band diagram, band structure basically you calculate, and then whether that is falling on that in the direct band gap or indirect band gap, then you will decide whether it will be a direct or indirect. Yeah. Okay, just let me know. Let me just open. Let me just try to enable the share screen option. Just setting. Video, audio, speaker, no. Meeting setting. Do you know where is the option in the Meet actually? I think now you can share the screen actually. Yeah, yeah. I can share see your screen. Yeah. So, huh. Can you zoom it your screen? Uh, yeah. This graph is given. Yeah. So, what is your doubt? Okay. No, actually, like lot of people get confused in this. So basically, this is so. So, uh, did you study that minority carrier injection profile actually? Yes, sir. So basically, this graph is like that. So so let me just give a brief outline. Uh, yeah. So let's say you have this piece of semiconductor. So my screen is visible, right? No, no, I think it's not. Let me just take a screenshot of your screen and just yeah. Let me just uh, okay, okay, yeah, yeah, sure. Just solve this first. Then you can solve. Yeah. So let me just copy. So now is my screen visible? Yeah. So now this is your this question is visible, right? So basically, what happens is so yeah. So what happens is like if you take a piece of semiconductor, Actually, if you shine a light or inject a minority carrier somewhere from like this left side, so what will happen if you consider a generation recombination? So what will happen? So you need to solve the drift diffusion equation. So basically, if you shine a light, then some carrier will get generated, and like this carrier, there will be two phenomena will be happening. One will be like those, let's say those electrons and holes. Let's say this is n type semiconductor. So the hole will be minority actually. So now, as you shine a light, electron hole pair will get generated. So it will have a equilibrium number of holes. So it will have a p n naught. You call as a in the n naught. Naught means for equilibrium. P for holes. So basically, equilibrium, it shows that equilibrium number of holes. So equilibrium number, there will be very high number of electrons because it's a n-type semiconductor, and very low number of holes actually. So this scale, and you see like that doping, if you do 10 power 15, so there will be around 10 power 15 number of electrons actually. And here actually this the number of holes will be ni square by na, which is equals to 10 power 20 divided by 10 power 15, and which will be equals to 10 power 5. So you see like this 10 power 5 number of holes, 10 power 15 number of electrons. So you see there is a 10 order of magnitude difference in the concentration. So in the concentration of holes or electrons. So this graph you cannot plot on linear scale. So basically you need to plot on log scale. So this concentration which you are provided, it's on log scale actually. So then basically and the other thing is, so like if you start generating this if you shine a light or inject some minority carrier, what will happen there, like the as the carrier will get diffused to right side, because this side has a lower number of carriers, and like the this effect will be more for the majority charge carrier, because minor more for the minority charge carrier, because majority charge carriers are huge in number, so the diffusion will be slow actually, because minority charge carriers are large in number. So based on the light number amount of light you have injected, there will be delta p and delta n, which will like the uh, which is the like an excess whole carrier generated, and that is equals to the your rate times the lifetime actually. Tp equals to the rate of n times the lifetime of electron. So basically this number of excess carrier electrons and hole pair will get generated, and like if this delta p is larger than p and naught, you will see huge gradient in major minority carrier. But majority charge carrier generation delta n will be much less compared to delta n will be much less compared to your n actually. So you, in that case basically you will take the effect of only minority carrier injection, because majority there won't be any much diffusion effect will be. So basically in this you need to solve the this drift diffusion equation. So that is equals to double derivative of delta p by with respect to delta x square equals to minus that so basically you need to calculate that drift current plus diffusion current equals to 0. So then that basically it will be a minus it will be a g times some so that will be equals to some k times delta p naught, and delta p naught you can write g times tau n or tau p. So this is for and as you can see this is a second order linear differential equation, and you can get the solution of this actually. So if you solve this, then you will get this profile actually. So delta px profile will look like this actually. and this is in the log scale. So is this like partially clear or somewhat clear? Yeah. Am I audible? Yeah. Yeah. Hi, AJ. Yeah. Yeah. Sorry. Yeah. Yeah. Huh. Okay. Huh. Huh. Then what will happen? So basically, how it vary? Okay, so basically, like when you reverse bias actually, so you will see like as you reverse bias, so this the profile is looking like this. If you reverse bias the junction now, so basically this the minority carrier profile will look like this actually. So basically that means that minority carriers are swept away from the junction. So it will in the forward bias you have the excess minority carrier compared to the equilibrium concentration. The carrier profile will like to, but in the reverse bias actually minority carrier will be pulled away actually to the bulk actually. So your profile will start looking like this. This is obviously on log scale actually. So this is your delta profile actually. So this means that your minority carriers are just swept away from your junction actually. So in this case actually the basically the uh, this p type charge carrier will get diffused and they will follow this profile. If you apply a positive bias, this profile will go like up like this, and as you keep reducing bias, this profile will keep go down. In the reverse bias it will go down actually. That's why you see like after some time it will become zero, and the slope it will, you can calculate the reverse current from this also actually, the slope of this and slope of this at this profile. Okay. So you can go for and basically like there are in if you go to the books like different kind of book actually, different different types of diodes are there. So like long base diode. So this is the exponential profile is possible for long base diode actually. So what is the long base diode? Actually, in this P and N region, if this length of P region and length of N region is L of P and L of N is much larger compared to the diffusion length for p-type carrier, LP, and diffusion length for n-type carrier. So basically, then you can approximate like this profile will be approximation, and also there are some kind of short base diode kind of thing. So where this Ln is much less or equivalent to the your diffusion length, then you can approximate this curve by linear actually. So there the profile will look like linear. So those are the cases. Like I think it's covered in I think SMG and like those Donald Lehman and those kind of books also it's covered. So basically you can consider different kind of cases, but for first level of course like this like the we assume that this is a like assumption of long base diode. So I hope this answer your question. Yeah. So, AJ, is this answer your question? Right. Uh, N region is highly diffusion. Yeah. Uh, large no diffusion length is actually it's a material property. So this diffusion length LP is basically equals to dp into square root of dp into tau p, and dp you can calculate from that Einstein relation. So dp by dn equals to uh, kt by q actually. So this is kt by q. So if you know the diffusion length of electrons, then diffusion length of holes is also fixed actually. So based on this and this uh, the based on the tau p and lp, this follow this relation actually, especially in the huh, huh. Yeah, you can say yeah. So which so basic so basically see like this profile is of this exponential of minus x by l of p. So if XP is large, then you will see this decay will be slower. So your profile, if you have a larger diffusion length, so if your LP is large, so you will have slower decay actually. So and if you have LP is small, then basically LP is what does it signify? Like approximate at much what distance the carrier will diffuse before recombining actually. So let's say you injected the carrier, but like the minority carrier, but they will recombine actually. So at what distance they will diffuse before recombining it. So for larger diffusion length, basically carrier wind won't recombine actually. They will penetrate deep into the your bulk region actually. So that's what this tail is specified. So larger the diffusion and larger this profile, it will follow like this. So this, if you increase the LP, this you can like plot it also. So you take this equation and you just plot in the MATLAB or Python or any tools actually. So if you for this see like this, um, so so now so this so basically you can calculate like uh, the so this no, Einstein relation is dp by mu p equals to I think kt by q equals to dp by mu n, and I think DPY, something sort of this. And yeah, so is that clear? Like, so if you have lesser diffusion length, then you will follow this sharp profile actually. Carrier will like recombine uh, very fast into the your bulk region. Is that answer your question? Okay. So you have an other doubt also. Yeah. So basically, P region, as you can see, P region tail is the longer. This region tail is the smaller. So P will have smaller diffusion. P will have larger diffusion. So LP will be much larger compared to LN. Just so no, no, yeah, N region. No, no, this is so no, no, this sorry, I made a mistake. So this is the let me correct. So this is the diffusion length of minority charge carrier, p type of carrier in N region actually. So you are considering minority carrier diffusion. So in N region, minority carriers are holes, and P region minority carriers are electrons. So this, as you can see, this trails are larger compared to this tail. So this N region will have larger diffusion length. So that is correct option. Did you get it? Okay. So basically, it's see like this. Let me just undo some part of this. So let me just, yeah. So this is the tail, right? So as you can see, like this has the larger tail. So let's say like normally how you define this exponential decay is by the time constant. If you are taking time by you define the characteristic time. So you must have heard the studies those LC circuit decay. So basically the in time is related to minus t by tau p. So how much like the at t equals to tau p, the your decay will be around 63%. Similarly, in X, it will be equals to LP. The characteristics times are the diffusion length or those length. So as you can see, so for this region, like the this width is this one only. So if you consider this and this, for this region, this width is larger compared to. So as you can see, in this region, carriers are like traveling much longer before recombining actually. So that's why this region has a uh, larger tail actually. So if you reduce this, so this if you reduce this, then exponential will become more stretched actually in this direction. So that's why like because this stretch in large in n region compared to p region. So your n region has larger diffusion width. You get it now? Huh, so 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 basically, if you want to define this characteristic diffusion length, then basically at what distance your carrier become 63% of what you have originally. So if you consider this as a delta p naught at zero location, if your delta p naught here x location, let's say x equals to lp, it is if it is has become 0.63% of or it has decayed 37% of your delta p naught, then basically that is your diffusion length. So if you more this length, the lesser is like more is the more this length, more is your diffusion length in this region. Is that clear? Okay. Thank you, sir. Yeah, sure. So any other person have any other doubt in any of the assignment? Yeah, yeah, you can ask like so it's better to clear. Yeah. Which week two, question number third and question number fourth. So yeah, this one, right? This one, or you are talking. Okay, so can you paste that one also? Ah, you can share it. Yeah, can you make it full screen? Yeah. Let me take a screenshot of this. Yeah, let me take a screenshot of this. Yeah, so is this question visible? Let me do. Yeah. So this question talks about A particular intrinsic semiconductor has a registry of 100 ohm centimeter. So 100 ohm centimeter, rho is given as 100 ohm centimeter at 300 Kelvin, and 10 ohm centimeter at 330 Kelvin. If the mobility of the charge carriers, if the mobility of the carriers and energy band gap remains the unchanged temperature, the band gap of the semiconductor is. So, so basically, so yeah, so in this basically, so basically, so you can calculate the like you have the resistivity. So you can calculate based on this. So based on this resistivity. Just wait. So yeah. So now basically resistivity. So your conductivity is given as NQ mu n, or for mu n, or uh, nq mu n plus n p q mu p. For intrinsic semiconductor, n equals to p equals to ni. So that you can write as n equals to p equals to ni, so that uh, your conductivity will become ni times q times mu n plus mu p. So this resistivity is given constant, and then basically the resistivity is just inversely proportional to the conductivity. So you are given at like the resistivity at 300 Kelvin, resistivity at 300 Kelvin, and resistivity at 330 Kelvin. So basically, if you take this ratio, then it will be equal to conductivity at 300 Kelvin, conductivity at 330 Kelvin. So this will become conductivity at sigma at 330 divided by sigma at 300. So now you can now, because mobility and band gap is given as constant, this will be equals to proportional to Ni at 300 Kelvin divided by Ni as 330 Kelvin. So based on this, so this left hand side is given. So the you can calculate the band gap basically. So different temperature is given, band gap is given as a constant. So an Ni expression you can take as like this. This and other constant factor will get cancelled. Only this factor you need to take. Will you be able to solve this? Yeah, just figure like I don't numbers. I Yeah. Temperature is given at two different temperatures, and band gap is given constant. So basically you can calculate the ratio, and that with that ratio actually you can calculate. So let me just calculate. So Ni is given as temperature of, so it will be equals to so it will be equals to so your temperature 300 Kelvin. So it will be equals to your 300 Kelvin power 3 by 2 exponential of minus Eg is given divided by K times 300 Kelvin divided by is 330 Kelvin 3 by 2 exponential of minus Eg by K times 330 Kelvin. Then you can take this exponential term. So this will become 300 by 330 power 3 by 2 exponential of minus Eg by Eg will come common, Eg by k will come common, and you will remain. So this will become 30 by 330 times 300. So basically from this and that you are given as 330 is given 10 by, so left side term is 10 by 100. So it will become 1 by 10. So 1 by 10 equals to 30 by 33, uh, 3 power 3 by 2 exponential of minus Eg by k times 30 by 300, 330 times 300, and you can calculate, even you can simplify this further. So basically you need to find Eg from this. Will you be able to calculate? Yeah. Okay. Okay, so you can try it parallelly. Let me, if you have any other doubt. Fourth question. Consider a silicon doped with a boron uh, to a concentration of 4 into 10 power 15. If Ni is this, and Vt equals to Vt equals to 26 milli electron volt, uh, compared to the undoped silicon, then the Fermi level of low doped silicon. So basically, this you can just calculate. So this you can calculate basically. N equals to Ni times exponential of Ni times exponential of EFN minus EI by KT, and this is so basically you are given N. So N you can put as 4 into 10 power 14 equals to Ni is given as 1.5 into 10 power 10. So this is 1.5 into 10 power 10 equal to exponential of EFN minus EI by 25 milli electron volt. So this you will calculate EFN minus EI will be equals to KT by Q ln ND by NI, and that basically equals to 26 milli electron volt times ln. This will be equals to 4 into 10 power 50 divided by 1.5 into 10 power 10. So this will become 26 millivolt times ln. So this you can simplify. So 4 by 1.5 times 10 power 5. So this, if you calculate this log, then you will find that like that like this is the gap is solving. So basically, compared to the undoped silicon, undoped like so for undoped silicon, the Fermi level will be equals to the Ni Ei equals to. So with this equation, actually you can calculate the Fermi level of doped silicon with respect to undoped silicon. Is that clear? Okay, so basically, yeah, so how it goes towards to EC and EV. So basically, uh, so uh, uh, see like this. So this is the relation. So you there are multiple ways to find that which side is same. So one way is one way is just use this relation. Actually whatever I have given, use this relation. So as you can see, so this uh, n equals to ni times exponential of EFN minus EI by KT. So as you can see, Ni is around 10 power 10 and N is your 10 power 15. So it is much larger. So this exponential factor should be much larger compared to your much larger compared to 1. So that's why this EFN by this must be quite greater. So this will be positive actually. This should be positive. So this factor should be positive, and so this EFN minus EI should be positive, greater than 0. So this means this EFN should be greater than EI. So the equation wise you can understand from this actually that your Fermi level should lie above compared to EI. So and other ways to calculate. So so in the n type semiconductor, other method to calculate basically. So let's say this is EC and this is EV. So you have a distribution of density of states, and basically so if you are considering an intrinsic semiconductor EI, which the band gap lies in between. So basically you need to draw the Fermi direct statistics basically on y-axis. So if you draw the Fermi direct statistics, so it will follow like this. So this so it will follow like this. So yeah, so this will be is equals to this EI will be equals to EF level. So to calculate the electron concentration, basically you need to multiply this density of state times this band tail of this Fermi direct distribution. And if you multiply that, so it will follow in the conduction band, it will follow like this. Valence band also this will follow like this. So now for n-type semiconductor, you have more number of electrons. So so uh, the number of electrons is the area under of this curve actually. So this area is your number of hole p, and this area is number of electron n. So to to have larger number of area to get so for n type semiconductors, you have larger number of electrons compared to larger number of holes. So basically you need to shift this statistics up to get this curve more. And like if you shift this Fermi direct statistics to this up, so this tail will lie further, and basically this tail will like this, and this side this tail will be low. So basically this side the area will look like this, and this side this area will look like this. So this area will be smaller, this area will be larger. So that's why this Fermi level should move up actually. So is that clear actually? So that's why it should move up to maintain that equilibrium statistics actually. Yeah. So did you able to find that answer to your previous question, or so it's Eg by 2. Yeah, sorry, it's Eg by 2 actually. So this is Eg by 2. Yeah. So sorry, I made a mistake. So it will be Eg by 2 because huh, for what? Find which push. Huh. Hmm. At the place of Ni. So Ni, no, Ni you just put the temperature you given. So see like the uh, so basically rho at 300 will be proportional to Ni at 300. So because Ni is proportional to temperature, so Ni will change at different temperature, and your conductivity or resistivity is different at different temperature. So basically, so uh, rho at 3, so this relation will get rho at 300 divided by rho at 330 equals to Ni at 330 divided by Ni at 300, and Ni is governed by this equation. So if you are provided by like some different Ni relation, then you put that relation actually. But this is this is the standard formula. So you take, actually there are some more factors related to Ni, but like for first approximation, you can assume this kind of relation. Because like the conductivity is proportional to Ni, resistivity is inversely proportional to Ni. It's inversely proportional. No? I have written here this resistivity inverse of sigma actually. Yeah, is that clear? Yeah. Okay, so any other doubt you have? Okay, so any other person or all other people you have any doubt? Uh, yeah, like from any previous assignment which I have solved or which you solved in the class, you can ask actually. There is no limit today actually, like because I think all your deadlines are over. So yeah. So which region should you should follow for better marks? Which book? Okay. Hmm. Okay, so basically, like as per my understanding, uh, like this photo detectors areas are quite important, and uh, in that sense, actually, like the especially those PN junction and basic kind of, don't try to learn too much high concept. Just focus on your basic. I think you can master all the questions. So I think the proportion will be like in the exam. Each week, depending on the week, there will be equally proportional of questions. So, like easy scoring area, maybe PN junctions and these kind of questions you can follow actually. So, not in very advanced kind of devices, kind of like everyone, like the question will be basics, focusing on basics. So all the basic topics you should follow, not very advanced like finfet and those kind of things won't be asked. Like if those things were discussed, I think those like some historical question for 1 or 2 mark may be asked, but not very deep kind of question like the PN junction and those basic kind of questions. That frankly I don't have idea, because like we don't have like much communication with the like current like the instructor TA and like VTA are like two different entity actually. So like the like those TAs are separate, I think, or instructor may form the question based on the like. But you like it will be sure, it will be pattern will be more or less similar to the previous year pattern. So, so yeah, at most it will be mostly like integer type question, like similar to ask whatever asked in the gate or so integer or fraction. Yeah, so even that nowadays, even gate also like like they allow a limit on what approximation they will do approximation like some round of value you need to put answer. Yeah, so that will be the mostly the format for exam. If you have access to previous year exams, you solve those previous year question at least. Yeah. So the pattern will be similar. It won't be much away from the previous year exam. I think let me just see if I have previous year. Uh, okay, let me just see if we have access to previous. Uh, uh, Even I think I also don't have previous year questions access actually. Yeah, click V0. No, I think review assignment progress. I also don't have the previous year questions actually. No, I don't think I have. Uh, mm, Progress. Uh, no, I don't have access to previous year. So previous year Anthem paper I don't have. Previous year assignment problems I have. But you make sure like if you solve this previous year assignment and current year assignment, even a decent level, you will be able to crack it. Don't worry about it. So just be clear on your basics actually. So like mostly questions, if you can have decent basics, then don't worry about like you will be easily will be able to manage it. Yeah. Any other doubt you just figure out like if you have uh, any doubt hits to your mind because I think we are just 2 days away from exam, so like you must have prepared quite nicely for that. If you have any doubt, even theory doubt, you can ask it, not just question. For what? Mhm. If there is, okay. Mm, if you your question is if you face any doubt, can you mail me? Okay, so let me write my mail ID, but don't make it public, otherwise I will get unnecessary spam call. So just write like if if you have any doubt, no, there is not. Let me just it's sorry, someone yeah. Yeah, so I have posted my mail ID, but don't share it publicly. So yeah, so if you have any specific doubt, you can mail. I will maybe reply before like Like I will try to reply. But I may also be traveling by 24. I am traveling, so like I will be in some flight, so that time I may not reply. So, but like after that, I can reply. Yeah. So, uh, if you have any like if you have any doubt later, you can ask or uh, like I think then I was thought like if you could not have doubt, I would have covered this like the energy band diagram for different type of heterostructure you can draw. But I think now we are it's already 20:30, so I think we have only 50 minutes. So let me give a brief like you can take like this was the fairly basic level course. So you can take higher level course like related to specifically optoelectronic devices and compound materials. So where in that course basically you can study those like those no, those heterostructures or heterostructures and compound materials, and that those especially focused to optoelectronic devices like LED lasers, photo detectors, different kind of photo detectors, different material systems. So there is a comprehensive course you can find. Like if you take those courses, then those are the courses like which require this course as a prerequisite, or you can take some transport courses, quantum transport or physics of nanoscale devices or nanoelectronic devices. Those courses also some bit advanced level course you can take from based on the learning in these courses. These are like few courses you can take, and like you can like yeah you can like based on this foundation you can take a number of courses by this foundations. So uh, yeah, so I just wanted to cover like you can draw the band diagram for heterostructure. So basically, let me draw the band diagram for one type of heterostructure. So basically, so till now in the course, even this course, like what you studies was the N and P side was the same material actually. So there is a parameter known as we discussed this electron affinity. Electron affinity. So that chi. So if your material is same, that chi is same. So basically, you were dealing like the band structure which has this kind of band diagram. So you were dealing with the suppose this is the vacuum energy level, and this is your interface, and in your case actually, and till now we were discussing the problem which have the case like this. So this uh, electron affinity of p side or electronic affinity of n side was the same actually. So now only the difference was this n side was this the Fermi level closer to the conduction band, and the p side was the Fermi level closer to the balance band. So basically, if you draw the balance band like this, so this so this level will have the balance band. This is the ef of p side, this is the ef of n side. So now to draw the equilibrium band diagram, you need to so now this is the non-contact band diagram. Non-contact band diagram. So basically you draw the band diagram with respect to the energy of the vacuum level. So when you don't make the vacuum level, you don't make any contact. Vacuum level energy is flat actually. This energy is flat. So now when you make the contact actually, so now after once you join the semiconductor, so that means that your Fermi level in p side equals to the Fermi level is p side equals to the Fermi level. And basically now you can draw the band diagram based on this. So in the bulk, the Fermi level will be closer to valence band. In this, basically the Fermi level will be closer to the conduction band. And if you can draw the conduction band here, conduction band, valence band here. So if you can join this line to draw the band diagram, you can join this line corresponding to the diffusion. This was your band diagram, because uh, and corresponding to this, your band vacuum level banding equals to the your built-in potential, it will band. But in case of heterostructure, actually your let's say this kind of let's say you have two different material in the p side or n side, so they may not have the same electron affinity. So let's say even the band gap may also be different. Let's say one material has a band gap like this. So one material has a band gap like this, and other material has a band gap like this. So this has a smaller, so this is Eg2 and this is Eg1. So and this is chi2 and this is chi1. So as you can see that chi2 is greater than chi1, right? So so now, and Eg2 is less than Eg1. So now this band diagram is there. So to draw this this kind of complicated band diagram, so first procedure is you draw the level with the non-contact band diagram. On contact band diagram, so you draw the vacuum level. This is vacuum level. Vacuum level as a flat. You draw the and the this electron affinity is material dependent parameter, material and composition dependent parameter. So for a particular material, this will be a fix. So you draw the conduction and the conduction band just below the this chi energy level. The based on the electron affinity, you draw the conduction band of the those two levels, and you can draw the band valence band based on the energy band diagram based on the band gap of the material. And you can draw the EFN and EFP based on the, so this is EFP and this is EFN. You can draw the band diagram, the Fermi level, how much is the concentration of electrons and hole with respect to. So now now and because this, so in the band diagram, basically this gap, actually the this EC of P at interface or at junction, uh, so so that this gap will be constant. This gap also will be always be constant because this is material dependent. So at junction, EP, so EC of P side minus EC of N side uh, uh, will be equals to this delta E. So this is delta E of N, delta EC. This is known as the conduction band offset. Similarly, EV of P side minus EV of N side also will be constant delta EV of V. This is the valence band offset. So since this we derived from the material dependent parameter, so when you join these two pieces of semiconductor, this parameter will be a constant. So now when you want to draw the equivalent like equilibrium energy band diagram, so you draw the common Fermi energy level. So this EC of N, EF of N equals to EF of P equals to EF. And then basically now if this is the junction, so then away from the junction, basically your this side will be a p side, so that you can draw like this, and away from the junction this will be a n side. Similarly you so similarly away from the junction in this region, this will be a N types semiconductor, and this will be a P type semiconductor. And your like you see like this EC, like the P side has higher uh, 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 I, like this delta EC will be a constant at junction EC minus this will be a constant. So in this kind of semiconductor, actually uh, you will see a sudden jump in the this level. So basically, you will see like this and this kind of. So this is like a delta EC, and similarly you will see a so just wait, I think so this is the smaller band gap material. So this is the smaller band gap material. So this level will be much smaller. Yeah. So now, and this as you can see like this band was negative, so even after that also it will remain like that only. So this band yeah, yeah. So no, just I made a mistake. So I made a mistake of a mistake. So yeah. So basically, like this is your non-equilibrium band diagram. So to have the equilibrium, so basically this EF, if the n side is lying higher, so this will move go down, and this will go up actually. So so finally you will draw this conduction band, uh, the Fermi level as a constant. So this is EFN equals to EFP equals to EF, and then this suppose this is the junction. So this is the junction, and if you draw this in the bulk, you draw this as a N type. So you draw this as a conduction band, and the in the this side it will be a P side, and basically uh, you draw is a the and you draw the conduction band corresponding to this, and you draw a conduction band corresponding to this. Now basically in the equilibrium you need to join this bulk. So the other rule is that delta EC and delta EV is flat. So basically, now basically, so this side band will be pulled down. So basically, it will be like this. So so if you join like this, there will be a constant conduction band offset, and this is the EC of N. Similarly, in that case, and here also it will behave like this, and so here also it will behave like this. So uh, so here it will look like this. So uh, here also it will go like this, and then you will see an offset, and then you will see a join. You need to join this. I did not draw it proper, so this notch it will form actually. So this is EC of P side. So I did not draw it on scale. Let me just draw it. So this basically, if you draw this on scale, then you will see like this level, and it will follow like this. So this kind of and this EC minus EC minus EV will always be constant. So this kind of notch and those kind of uh, certain band offset will be there in the heterostructure kind of band diagram. So this like for different type of band structure, so like there are different type of band structure. You can draw the band diagram for this. So like this depending on this your electron affinity, your like this. So electron affinity of right side is larger compared to the electron affinity in left side. So for that, different kind of band diagram is there. And electron affinity of left side is larger compared to electron affinity of right side, and the band gap is also larger in the left side. Then you can draw the diagram. Also, the other type of so this like this kind of structure, different kind of structure. This has a naming actually, like this type 1, type 2, type 3 kind of structures. Its naming is there. So those intricacy you don't need to understand, but like the basic band diagram you can understand. So is there any doubt in this? So is this things are clear? Yes, sir. Okay, fine. Okay, yeah. So, this is the like future course. You if you take with the history structure, then you will find this kind of band diagram, or you can practice by your own. So, if you have any other doubt, just email me with that. Uh, I wish you good luck for your exam, and thank you so much for patiently listening this session and all the session throughout. And you keep enjoying learning. And thank you so much. It was nice to have a discussion with you guys, and you were quite nice in like patiently listening those sessions. And yeah, I wish you good luck in your life, and I hope you enjoy learning like whatever you want to learn. So thank you so much. If you don't have any other doubt, then we can end this session. And uh, typical feedback I already have taken from you guys. So thank you so much, and have a nice nice time and enjoy your life. Yeah. Yeah. Yeah, thank you so much for your comment. Yeah, I also enjoy clearing your doubts. Yeah, so it's a great learning for me to how to communicate, how to understand your question better. So yeah, so thank you so much. I deeply feel gratitude for your like this session, and thank you so much, and have a nice time. Yeah. Okay, so I think then we can end this session. So thanks a lot for your patience and hard work. So yeah. So if you don't have any doubt, then we can end this session. Bye. Have a good night. Have a nice weekend and nice exam.